Hey, welcome. Good to see you again. Have a look at this. I've got a few representations of categorical and discrete data, and some of this you might have seen before. And here's a saving feature down here. We have a calculator, and quite a bit of this work in this course will be done using the calculator, which is good news, of course. Okay, let's look across the top. Have you seen some of these before? These are column graph, a horizontal bar graph, a pie chart, and here, if you like, a subdivided bar graph. Okay, so these are some of the things, some of the ways we represent categorical data. Can you see the categories over here? Aussie rules is a game, netball, rugby, cricket. So they're all categories, and this is the number of people, when we surveyed them, said that they played those games. So that's the idea. And over here, let's look at the pie. Remember here, you divide up the pie in proportion to each of the numbers of the games that the people play, and what you need to find is a percentage in each category, and then find that percentage of 360 degrees. Don't you? Do you remember that? I don't know whether you've done that. We've got 360 degrees, and we've got to carve them up in proportion to the percentages. We'll see that on the calculator as well. The same thing here. We've got to divide up a certain length of line. Here we are, the length of the line, into a percentage or a fraction equal to how many play each of these games. So it's a fair representation. So that's the categorical data. And that's the data that we're representing in this table here. And this is the usual way we collect and display the information. Okay, what about down the bottom? Down the bottom, we've got the discrete data. Discrete meaning that you have separate numbers that you have measured. So it's similar to categories in a way, because you can't have anything in between. Can't have anything between 3 and 4, because this is the number of eggs laid per hen. So they are distinct or discrete values, and then they have a frequency. So it's similar in a way to categorical data. But the big difference is, of course, it's got numbers instead of categories. So it's numerical, or sometimes called quantitative data, because you're looking at quantities, the size of them. Okay, and then, of course, another way of representing that, so this is a column graph over here for discrete data, and another way is to represent it with a stem and leaf plot. Okay, so our actual measurements there represented as a stem and leaf plot. But we'll look at that one a bit later on. Okay, come down, let's get started and see what you think. I'm going to start you with the calculator now, because I know people are keen to do that, and you need to go into stat mode. I'm going to be working here with a 9860 Plus graphics display calculator. So we go to menu and choose stat mode, and you get this opening window, and in that now I've put the data that we've measured here. So it's the categories of the games that people are playing in each of the games. So we just put in 1 through 6, because there are 6 different games, and in here we've entered the numbers who play each game. I don't know whether you realise you can graph that. So if you hit F1 under here, you'll choose graph, and we get this window. Okay, and so we need to then hit F6 to get set, and up comes this window. What sort of graph do we want? We're going to list that in there. Now I'm going to choose a pie graph, so I want to change this scatter to pie, so I'm going to hit F4 there. I've cut that out, making it just a little screen clipping of the window of the calculator. So I'm going to choose that. So I come across here now, and I've chosen pi, and I've got to tell the calculator that the data is in list 1, which is where I put it, and I want it to display percentages and not store anything. So okay, if I hit execute, then I come back to this window, and I want to find graph 1, which I've just set up, and so I hit F1, and there's my nice pie chart. And the advantage of this is the calculator has already converted each of those scores to a percentage of the total. So maybe if you were doing one by hand, you might still use technology to produce these percentages, because then you'll find for Group A, 21.18% of 360 degrees, and that would tell you how big an angle to measure in there, and so on. Okay, I hope you remember how to work out percentages. Okay, so it's the percentage, 3 significant figures will do, over 100 times 360 degrees. So just watch that one. All right, what if we wanted to do a bar graph? Okay, so come back to the set menu from graph. Here it is, back up here again. We want to go exit back to set and change this pie to on the next window. So you have to go to the next window and choose a bar graph. Okay, this calculator won't give you a column graph for this set of data. So we do the same thing, bar. Data in one is list one. We can put several columns next to each other if you want to compare them. We don't have any extras there. So there's our categories of our sports played, and this is the number of people playing each one. So you can go Shift F1 and pop on here and trace it, and they'll give you how the frequency of each of those columns. Okay. Here's an interesting thing down here. One there, if you hit F1, I'll show you later on, this gives you the mean of the scores and so on later on there. Anyway, not to worry. Let's have a look now at the idea of that, and I want you to try some problems. So this is from Hayes Publications, Hayes and Harris Publications, and this is 5D1, and they're asking things like the mode. So when you made your table up, they want you to find which is the highest value, because the mode, I don't know whether you remember this from junior maths, the mode is the most frequent score, the one that occurs most often, or the group that occurs most often, if you've grouped the scores. Okay, so I would like you to go through these and try to do some elementary work there, and just getting used to reading frequency charts and drawing column graphs, pie charts and so on, like we just did. So have a go at those 4 questions and get your head around this representation of categorical data. Here it is at the moment, all categories. All right, let's go down and have a look at the answers. So if you haven't done them yet, pause it and then come down and have a look at the answers. Here are some answers for you. Okay, those 4 little questions. Just a bit of revision to get your head around how to represent data that might have been gathered. All right, let's go on and have a look at some more, and this time we're going to have a look at, I'll just go back up here a little and have some discrete numerical data. So we've seen the categories, now we're going to have discrete numerical data or quantitative data. So we have actually collected a whole lot of numbers. And the important thing here is that they're discrete, separate sort of counting type numbers. You can't have fractions or decimals in between. We're going to do that in a later presentation. So we've got all whole numbers. Okay, have a look here. They're all discrete whole numbers, counting numbers if you like. Okay, so this is a set of data. How do you organise this? We could see with our categories that wasn't too bad. What do you do when you've collected all these numbers? Okay, well, let's have a look. I think this is a set of data of outcomes of some experiment. I think it's, here it is here. Number of eggs laid. Okay, so we've looked at the number of eggs laid by a big poultry farm. So we've listed them down here. These are the discrete values, and this is the number of times we found, or the number of hens that laid that many eggs. So we go through and we look at the number of hens that have laid a particular group. Let's look at down here, the tally column. So when we find a hen that's laid 6 eggs, we put a stroke there. And then another stroke, another stroke, another stroke, 4. But the 5th one we lay down so that each bundle of 5 is easy to count up. Because otherwise you'd have a lot of these at the end, wouldn't you? That's too hard to count, mate. So we don't do that. Every time we get a 5th one, we lay it down and make a bundle of 5. So that's 1, 2, 3, 4 5s are 20, and 1 is 21. It makes it easy to count it up. So that tally column is a way of recording how many in each of the different values here, discrete values, we have. The number of hens giving that many eggs. All right, so then we work out 1 stroke, that'll be a frequency of 1, 2 strokes, 2, 4 strokes, 4, etc. So we get a frequency column. Now, we could draw a column graph with that, that's okay, but we can also make a relative frequency. So this is, if you like, the fraction of the total which are in each group, the fraction of the total. And if we multiply by 100, we could change that to a percentage, if you like. We could have percentage relative frequency. So we've got all these numbers, and we've gone through and said a 7 is down here. We put a stroke in this group. A 6, put a stroke in this group. Get the idea. So when we've listed our data, we tally it up, and then we do these calculations, if you like. We've got a frequency, and then a fraction in each group, a relative frequency. Let's see what we can then do with it in a graph situation. Okay, so we've got the two here. So we could just plot the frequency, how many are in each of the different categories here, well, not categories, discrete values, how many laid 3 eggs, 4 eggs, etc. Number of eggs per hen. So it's very important that you label the axes and also have a clear scale on each of the axes. Okay, these are important so that people can actually understand the graph. And over here we've got the relative frequency, showing, if you like, the fraction, 0.4, decimal fraction, 4/10, or 40% were in up at this line, and 30% and 20%. So you can actually read off the level of occurrence of this number of eggs per hen. Okay, get a good idea. All right. This is quite handy if people have got different totals. They might have had 3,000 hens and you've only got 1,000. By changing it to a fraction, you can compare your results more easily. Okay, what have I got down here? Well, this is Casio again, and here we are in stat mode again, and this time I've entered the discrete number of eggs there and how many times the frequency in the next column. Now, this can't be handled by the calculator very well at all for graphing. So why have I put it there? Well, I'm going to hit this time Calc F2, and it comes to this window, and if you hit F6 to set it up, you can set up list 1 as the score and list 2 as the frequency. And then you can calculate, when you hit 1 there, the mean. So do you remember the symbol for the mean? The mean number of eggs laid is 7. Then later down here you can find the mode as well. Okay, so that's a calc thing on the calculator. I don't know whether you've done this before, but you have to set up this as the X list, the score, and this as the frequency when you go into set mode there. So you have a look at that a bit later on. All right, so what can you do now? Let's have a look at the sort of shapes of distributions that you might get. Now, quite often it's nice and even, and I don't know, was ours like that? Let's go back up and have a look. Oh yeah, not bad, fairly even on either side of a centre. And when you have that sort of setup, you might call it a symmetric distribution. In other words, there's symmetry. If you put a line somewhere down the middle, the two halves look like each other. It's like they're a mirror image, like this is a mirror here. So there's got symmetry, or it's a symmetric distribution. Well, what went wrong with these down the bottom here? Well, there was skewness. So skewness here means deviation or drifting away from symmetry. So where would this one have been symmetrical? That would have been nice there, wouldn't it? That would have been nice and symmetrical. So this is the problem area. So the negative side has been stretched. This is what's disturbing symmetry. So we call it skewed negatively. So you go to what is upsetting the skewness, and if it's on the negative side, remember on a number line, that way is negative, and that way is positive. So we can say what's disturbing our symmetry. Here's a nice patch, but over here, this is disturbing it. So it's skewed or disturbed negatively, or to the left, or low. Any of those could be used. What about over here with the positive ones? This is a bit symmetrical here. What's stuffing it up here? What's messing it up? This is this region here. So the skewness, the way in which it's disturbed symmetry, is to the right, or on the positive side, or high. So we call it positively skewed, or messed up. So think of skewness as that part of the distribution which disturbs our nice symmetrical pattern. And you describe whether it's on the positive side or the negative side of the main symmetrical part. Do you get it? Maybe you've seen that before. So we like to describe to people that sort of pattern, if you like. Let's go down and have a look at the other type, which is quite frequent, where you get two modes. There's sort of two main areas which both occur more frequently. So this is called bi, meaning two, right? Bicycle and so on, two wheels. Modal, two modes in that distribution. So this is some of the language of the subject. If you want to be good at a statistician and be a professional there, we use this sort of language. Okay, well let's go down then and have a look at the next little bit. Here we are, talking about, we'll just go get rid of that misleading thing there. That's misleading, all right. So here's our distribution of the number of eggs. Now, we've noticed something here. There's sort of a symmetry here. But what about this one? It's an outlier. It's lying out from the main body of data. Okay, so here's our definition. You must know this. You might note that down. Outliers are data values that are either much larger or much smaller than the general body of data. Outliers appear separated from the body of data on a frequency graph. So later on we're going to talk about how much must that gap be before we say it's a strange measurement. Now, the way we deal with outliers is interesting. First of all, we examine, is that an error in measurement? Error in measurement. That's what we're going to question. Error in measurement. If it is, we discard it. We're not going to count in. An error was made. If it's not an error, we include it as just another value. Okay, we include it. The interesting thing about outliers, of course, I don't know whether you know, I think it was back in the 1980s, they found a low reading in ozone in the southern hemisphere. And at the time, they said that must have been an error, and they discarded it. It's a pity, because if they had investigated more fully, they would have found, yes, it was a bona fide measurement and should have been investigated. So before you discard data, you must always investigate it, because if it is an error, you will not include it in your analysis. It's an outlier due to error. But you've got to make sure that it is an error. All right, come on down and let's do some. Okay, here's what you must not do. Okay. All right, misleading representation or presentation of data. I want you to pause the presentation for a little minute now and have a look at these two diagrams. And can you see what's been done and which one is a fairer indication of what's going on? All right, here we go. Let's have a look at this one. Somebody is pushing the idea that profits have skyrocketed, okay, between January and April. Have a look at the scale here. They have started off, there should be a gap there, shouldn't there? On a scale like that, we show that we've got a gap from naught. It doesn't go down to naught, only goes down to a little bit under 14, giving the impression that there's a much bigger increase between these two than what you might think. Over here, come over here, look at the scale here now. It goes as a proper scale starting at naught with no breaks. And now you see it isn't such a big difference in relative to the base figure, because this month here in January had a base figure of about 14.5. And compared to that, the actual increase is not that great. This representation over here is giving the impression that overall it was a much bigger increase. But it wasn't, if you remember, that January was quite big anyway. It was up to 14.5. Okay, false impression. So you shouldn't misuse statistics. People do, but that's not fair to the subject area. Okay, let's have a look at another one. Shopper preferences. 2 charts. Which one is fairer? Pause the presentation and have a discussion. What do you reckon? Can you see the difference? Okay, come back now. Have a look at the scale here. Starts off at 20, 40, 60 as it should be. Oh, what have they done here? They've changed the scale. 1 square there now represents 10. And that's produced a big height difference here. It's out of scale. When you put it back in scale, 20, 40, 60, 80, that's a consistent scale. Now B does not seem as much bigger than the others. Oh, that's very naughty. Okay, so we can't do that. Any scales must be following the mathematical convention, and it can't change along the way. All right, what's another one? Have a look at this one. See what you think here. Now, what's misleading about these? You might pause the presentation and study it carefully. Okay, we haven't got a scale up the side there, so it's not that. What is it? All right, come back now. And this time, mathematically, we should only be representing the values on the vertical axis there. We've got a little, psychological game playing here, because we've made this a larger cylinder, which has actually got nothing to do with the mathematics. Okay, if you look at them across here, the height differences are the same, all right, for all these. But this gives the impression, and this is definitely misleading, and deliberately so, of being a larger cylinder, therefore it's much better than fizz. When really, it's only, it's twice the sales there, but this can suggest it's a lot more than twice because of the volume in here. Psychologically playing games there. Okay, so you don't bring this into play. You must work mathematically with only scales and similar looking, like this, columns. Because the width of the column in this, what is this, categorical data, has nothing to do with the mathematical analysis. Okay, so that gives you some ideas of what you should be looking for when people are advertising, and things that you shouldn't do as you get to be a qualified statistician. Okay, let's go down. Here's some exercises for you. So, we're talking about whether these values are discrete or continuous. Okay, discrete means separate whole number values. Continuous means you can have values in between whole numbers. Okay, pause the presentation, have a go at question 1 and 2, and you can scroll down in a minute and mark your work. All right, I'll show you question 3 and 4. Oops, can't quite get 4, so let's just go back up to 3. We'll do 3, trying to interpret from the graph now. Okay, pause it, have a go. Let's go down to 4. Okay. Right, pause it, have a go, and now let's mark it. There's 5D2, question 1 and 2. And 3 and 4, just go down a bit more so we can get them all. Yep, 3 and 4. All right, how are you going? Getting the hang of the idea here now? Hang of it? Let's go on and do a little bit more. And here's group discrete data. Now we'll talk about this, very similar to other things that you've done in previous years probably. Now it's discrete data, so they're only whole numbers. But rather than list them all down, because there's a fair few of them, we're going to put them in groups. And we usually choose, if we're going to group data up, choose between 5 and 10 groups. Okay, and the idea of grouping would be there are too many individual scores here. So we'll bundle them up. 10 to 19, 20 to 29, notice there's no gaps there, 30 to 39, and so on. We end up with 6 groups. Let's tally them. Let's take the first one, circle it, 48. We put a mark down here in that group. 34, you put it in this group. Now, I've already done this. So you scan the data once only. Don't go through and pick all the 10 to 19s, 20 to 29s, etc. That's too time consuming. Read each piece once, read the data set once, and record in the tally column. That's important. Okay. Often these days, however, they scan data sheets that you might have compiled, and so this is a little bit old-fashioned here at the moment. Okay, and the tally, you want to tally them up. Oh, there's a bundle of 5. Right, by making our bundles of 5, it's easy to see that there's 10 there, 19, etc., out of our 30 pieces of data. So that's one thing that we can do. Now, what will we do with that? Let's have a look now, once you've grouped it up. So we could actually draw a column graph like this, with the frequency up here, clearly labelled, clear scale, and group intervals along here, and a label there as well. Okay, so that's important. Just notice now, once we've grouped it, we have lost information, haven't we? Because we don't actually know within each group how many of each separate value we have. So this group of 20 to 29, there are 5 entries in there, but we don't know whether that's 20, 21, 22, 23, 24, or what it is. We've lost the actual original data. So here, quite often people don't want to group data, but if you've got lots of scores, it gets very messy listing out every score. So we do group them. All right, can we do any more with that? Well, let's try something now. And I've got to put the answers there, so I'll just come down a bit, too close. So let's try doing that with this set of data. So you need to work out the group size. Well, the book's done it for you. Then I want you to do a tally and work out how many are in each group and do the answers to those questions there. All right, come down and let's look at the answers. I'll put them a bit close there. Okay, that's what you should have come up with. All right, okay, let's move on with this grouping of data and so on. And here's the alternative. The stem and leaf plot. Don't know whether you've ever seen this before. The big advantage of this is you use the raw data. You don't group it. Every score is recorded on the stem and leaf plot. Every score. But how do we do it? Well, first of all, let's look at this note down here. 2 with a stem 3 means 23. So what we're doing is stripping off the first number and using that as a stem value. So here our values went from 0 to 60, so the sums are 1 for anything bigger than 10, so this would read 19. 2 is in the 20s, So that's 28, 26, 27, 23, 28. So again, you read all the values and you record them. So 28 goes there. This would be 34. Then you might have a 26. So you put that next. And 48. So you go through and read the data once only. Okay, and record it. So this time, record it opposite a stem value. Okay, the tens value. Okay, because we are just abbreviating the score. Just notice here, that would mean 56. That would mean 50. This would mean 51, 54. So you detach the largest figure and then record opposite its stem value, the other figure. All right, that's what you do for a start, but then we want to put it in order. So come down and we put it now in order. What does that mean? Well, on each leaf, these are called the leaves, this is the stem, this is the leaf, it's in order. 3 comes before 6, comes before 7. So you might, when you're doing the recording up above on that previous window, you might use a pencil and rub it out and put them all in order, because this makes it easier to see what's going on. All right, the big advantage is you have all the original values available to you. You haven't grouped them and lost them. You can see that yes, there was a 49. There were 3 34s in there. Okay, so we should still have the note here, and that is 6/2 means 62. Something like that. Okay. All right, let's go down and see what we can do with it. Keep doing that there. Here are some questions. Can you do a stem and leaf plot? Don't know whether you've ever seen those before. Here's question 2 and 3. There's a stem and leaf plot given in this one, and the idea is to be able to read it. And just watch this. What sort of distribution is? Turn your stem plot on its side. Can you see any shape there if you put it on its side? Okay. How many? Is there symmetry? All right. What about question 3? You've got to do your own stem and leaf plot. So you've got to find the lowest value and the highest value. Okay. And they're telling you how to do the stems there. All right. Have a go and see if you can interpret the data using that form of graph. All right. Pause it, have a go, and I'll go on now. Question 4. Okay, again reading off a stem and leaf plot. All right. Just make sure with a stem and leaf plot, you do put that interpretation there. Okay, pause the presentation, have a go, and I'm going to show you the answers now, so you can mark your work. Okay, question 2, 3 and 4. So you're getting some idea now of the different ways of representing those two, I suppose the easiest sorts of data sets. Categorical data in separate groups, discrete data, separate numbers, very similar. Okay, well this builds up quite quickly now as you get more qualified as a statistician. This is a very important area of mathematics. People will like to know what's going on. They like graphs and calculations, but mainly graphs, don't they? So I want to leave you now. I'll catch you later, but cheers for now.